So welcome everyone. My name is Mark Berry. I'm the president here at Schoodic Institute at Acadia National Park. And we are here for a public presentation by Dr. George Jacobson, who is the Maine State climatologist. But we're also at the tail end of the Acadia Science Symposium. So I hope many of you have already had opportunity to explore a little bit at the many scientific poster presentations that are still up. We also had a great series of presentations and discussions here today. And this is the middle of a 3-day series of events. We had an art and environmental science collaboration workshop yesterday and another public presentation last night. And we're moving into a conference tomorrow with the Down East Research and Education Network called Convergence, that brings together conservation groups from across eastern Maine with education and research institutions and seeks collaborations in those arenas as well. We are going to open this evening with a 5-minute film that's a brief introduction to Schoodic Institute and our partnership with Acadia National Park. There are a few people here who have seen this either before or last night, but there are a lot of people here for whom it may be new, and we'll be interested in your feedback on that. And after the film, we'll go immediately into Dr. Jacobson's presentation, which I'm looking forward to. I think Schoodic Institute has an amazing and really unique opportunity because of the partnership with Acadia National Park, because of its setting, to really connect a lot of people with the natural world, to increase their understanding of issues that are increasingly important for all of us, and to really contribute in an important way to research in natural sciences.
When visitors come to Acadia National Park, we want them to learn about the values that are here and more about the actual resources that are protected. Schoodic Institute is a very important partner in helping us develop more programs and more initiatives related to science and education in the park.
The Schoodic Institute and the park work together at the Schoodic Education and Research Center, documenting the changes that are happening, understanding how those are impacting the park and its resources, and then figuring out how to best respond to those. My vision for the partnership between Schoodic Institute and Acadia is really that we work together to improve people's access and understanding of the science that's going on here, and also more generally, so that we provide a model that could be used in other national parks, other protected areas, and even beyond that, more broadly, to understand how to engage people so that they can understand what's happening and really make a meaningful difference.
The ability for the Schoodic Institute to work directly on site next to the National Park Service personnel, and for the two organizations to really bring their strengths together for one common objective has really worked out very well. I think it's been a real success story here. It really has a great opportunity to have a large impact on the Acadian region.
Schoodic Institute's setting is a huge advantage because the natural environment here is incredibly appealing. What has developed here at the former Navy base is, in my mind, very similar to a small, attractive college campus. And so you have this very nice campus with great facilities for many types of uses, set in the woods and set right against the ocean on one of the most spectacular pieces of the Maine coast. And that attraction makes it possible to bring top quality people working here and to bring lots of people here as visitors and as students. And I think that's a truly unique opportunity.
At Acadia, we have 70 to 80 different research projects a year. We're learning some amazing things. How do we communicate what we're learning to the public?
If you're having this research community develop and use national parks as natural laboratories, and they're phenomenal laboratories, of course, why not take that information and connect it directly to your education programs? So here at the Schoodic Institute, we're supporting the programs that bring school kids here, immersed not only in nature, but taught the fundamentals of basic observation and basic science, so that they're sort of self-propelled in their own observations and their own investigations. And once you get that bug, it can be a lifelong experience that people pursue.
As we grow and everybody's program starts to catch fire and have some strength, it brings in opportunities for different age groups, and some of them can do some collecting of citizen science, get some data that is useful for researchers. As those children get older and have more practice, the data they're collecting will be more accurate.
Having more knowledgeable people out there in the community about the resources in Acadia National Park means that those people are more able to help us not only protect the park for the long term, but support our efforts in making the right decisions.
National parks have a limited capacity to support science on their own. And what the Schoodic Institute does is it really helps us increase our capacity to support that science. So they work with us to be able to attract research, to be able to do research, to engage volunteers, and then connect that research with management actions and with education.
The future, I think, of Schoodic Institute and its role on behalf of the National Park is really limitless right now. I think that's one of the most intellectually stimulating and exciting parts of being involved at the Institute and of course with the National Park in general. We have the opportunity to impact at the international level, and we're really only at the beginning in terms of what we're able to do.
So today we heard a lot more about Acadia's research priorities in understanding and responding to rapid environmental change, and we had great presentations that delved into that locally and across the national park system and within surrounding communities. Different aspects of the issue, different aspects of how we are learning about it. And Dr. Jacobson is an emeritus professor at the University of Maine who is going to help us tonight in looking at a long history of environmental change and how that can help us understand current changes and future changes. And with that, I will ask Dr. Jacobson to come forward and take it from here.
Okay. Thank you, Mark. It's a pleasure to be here, and I appreciate the invitation very much. I congratulated Mark a few minutes ago on his new position here. I think it was a great choice for everybody involved to get Mark here, and I'm sure his tenure in this position will be a great success. I've had a chance already to run into a number of old friends and meet several new ones, so this is a great treat for me to be here. My wife and I drove down from Orono this afternoon and got to see some great Maine countryside along the way. But while we're here, I always have to say that this is one of my very favorite places in the state of Maine, the Schoodic Peninsula. I just love coming down here any time of the year, so I always appreciate the invitation. What I'd like to do today is spend the next 45 minutes or so, and if I drift on a little longer, bear with me. I'd like to give some perspectives on what we have learned in our research about long-term climate change and how those perspectives help us understand what's happening now and is likely to happen in the future. I came to Maine in 1979 to join a research institute that today is called the Climate Change Institute. It turns out it was one of the very first research groups in the country at any university established to study the Earth's climate, and it was definitely the first one that had scientists from many different disciplines together. There was one other at the time established out at the University of Washington in Seattle, but it was all geologists. Our group, from the beginning, has had biologists, several kinds of geologists, oceanographers, archaeologists, historians, computer scientists, oceanographers, if I didn't say that, all working together to try to understand how the Earth's climate system functions over time, and hence to understand the natural world better. And although we have research projects going on all over the world, and the red dots on this particular map indicate some of the sites that have been studied in the last decade or so by our faculty and graduate students and even undergraduate students from the University of Maine. And the projects are site-specific and question-specific, of course. But I like to think about the work that's going on today in our institute, which encompasses probably at least 30 or 35 different scientists from these different disciplines and dozens of graduate students. I like to think about our work collectively as trying to understand the question I've written at the bottom, and that is to understand the natural variability of the Earth's climate and the mechanisms that cause that variability. And I think that you can understand why it's important to do that. It's important because if we don't understand the natural variability and natural patterns, how can we put in context what's happening now or might be happening in the future? We can't decide whether what's happening now is unusual unless we know what usual is. So it turns out, when we started this back in 1972, our institute, we had the idea of trying to understand this, but we were thinking more about trying to understand what causes ice ages and how things work in that fashion. Well, of course, it turns out that what we've learned all these years has a little more immediate importance than we had expected back then. Mark mentioned that I'm the Maine State climatologist. I hasten to add that that is a completely voluntary position. I consider it an honorary position, similar to what the poet laureate might be. It's a great honor to be asked to be the Maine State climatologist, and it gets me invited to give lots of talks, similar to what a poet would, I guess. But I have decided, while functioning in this role since I retired back in 2008, to try to do things that help the state of Maine. And one of the things that we did early on was to respond to a request from Governor Baldacci, the governor at the time, who asked our institute to look forward to the end of the 21st century, the century we're in now, and to try to make a reasonable estimate of how the climate might have changed by then, and then what those changes might mean for Maine's ecosystems, what it would mean for the forests and for the lakes and streams and for the Gulf of Maine. And when those natural resources change, of course, it has big implications for our economy, which is also so based on natural resources and tourism and so forth. So being Maine, we, of course, had no budget to do that either. But I was able to put together a group of 75 colleagues who have expertise, serious expertise in all of these areas, and each volunteered to participate and share their insights about these different things. And we wrote a report called Maine's Climate Future that is about 75 pages long. It's I must say, well edited. It has wonderful illustrations, and it looks forward to the changes that might take place and how those will affect these systems and our economy. And then it looks for ways that we might think about adapting to the coming changes, because we need to be thinking forward as citizens of our communities and our state to thinking about how to do this. Based on very conservative estimates of how much the climate would change, and by conservative I mean we did not take a high estimate of carbon emissions. We took a very modest level of increases as our basis of analysis. So I think we actually underestimated what will actually happen. But based on those changes in atmospheric chemistry, we looked at a series of model results based on about 20 different climate models that have been used globally to understand the Earth's climate and the changes that might be coming. And I would say that those models taken together all suggest that Maine's climate is likely to be 7 to 10 degrees Fahrenheit warmer in all seasons in all parts of the state. That's a rough estimate, but that's a pretty significant change. It puts us easily to the climate in Connecticut, if not farther south, if you want to think of it that way. So, of course, if we have a Connecticut-like climate, we have to have very different systems here. Now, if we think about today's climate in Maine, we can think about it in lots of different ways, but I like this map. This is the new, as of 2012, map put out by the U.S. Department of Agriculture of plant hardiness zones. Now, this is one we're all familiar with. Whether or not we've all seen this map, we're familiar with it because when we go to the garden center to buy shrubs for perennials of shrubs or plants to put in our gardens, we pay attention to what the growing zones are. Because those of us who live inland a little bit know that just because something can grow well at Surrey Garden doesn't mean it'll do well in Orono, because the growing zones are different. Well, this map had to be redone in 2012 because the 1991 map that preceded it was out of date so badly that almost every place was at least one zone off because of warming that had already happened. But this is an interesting map about Maine, and I like this because it's an expression of really what winter conditions are like. That's what determines the limits of growth of many plants, is how severe are the winters. And we see here in northern Maine, as we all know, northern Aroostook County and the western mountains have very cold continental climates. We had a record set 4 or 5 years ago in northern Aroostook County of 50 below 0 Fahrenheit on one winter morning. That's a pretty cold day. And yet down on the southern coast of Maine, the climate is obviously much milder and influenced by the maritime conditions there. Here we are where I've put the arrow pointing at us here in Schoodic. But what's interesting about this is that we can see that there's a very strong influence of the ocean on this coastal part of Maine. We all know that. That's part of our environment. And when we think about winter conditions and a storm coming in, you know, those of us who live up in the Bangor and Orono area, for example, know that it might very well be raining or misting down here, but by the time somebody's driving from Winterport towards Bangor, that turns to snow. That's just a typical winter condition. And of course, farther north is a whole different story. And so here we have these mild conditions along the coast where the green pattern is. And this is based on the average coldest conditions in the wintertime now. Now, if we think about cold conditions, though we know these things are changing. Here's a headline from a paper in southern New England from 1905 talking about the New England harbors, the southern New England harbors, being so frozen that ships couldn't navigate in there. Well, that just doesn't happen now, of course. In fact, here's a photograph of one of the harbors on Vinyl Haven in 1918, another time very different from conditions we would expect today. It's almost unthinkable that we could have ice conditions that people could walk out on the ocean in anywhere along the coast of Maine. And yet, those of you who are familiar with this area probably know that there's a museum out on one of the Cranberry Isles that has a photo in it that shows granite blocks being pulled out there on a sled by oxen over ice early in the last century. Who could ever imagine that happening? I mean, it's just such a different world. Here's some data now. This is a figure showing the mean temperatures of December, January, and February. So the average mean temperatures of December, January, February, the coldest winter months in Orono. And as we can see, going back to 1890 and up to the present here, or almost to the present, we can see that there's definitely a warming trend. There's lots of year-to-year variability and spikes of different kinds. We know that, and we expect that. There always will be, there always have been lots of annual variability and decade scale variability and so forth, despite the long-term trends. But what's interesting here is that these really cold periods of the kind that would have produced those frozen conditions out on the Gulf of, along the coast were early in the last century, but the last coldest one was 1934, and that's the last time there was a lot of freezing in Penobscot Bay. Since then, there just have not been very cold conditions, and you can see pretty clearly that the cold conditions are quite different. Well, if we think about those patterns and put ourselves in the broader region of this Acadian forest, sometimes we could call it, that includes Maine and northern New England over the Adirondacks and then out to the Maritimes, we actually have a very interesting landscape from a conservation perspective, and I think all of us here tonight are interested in that. We have an area that has a somewhat similar type of vegetation and actually a lot of forest cover. So we have conditions that are amenable to having fairly healthy ecosystems that are accessible to plants and animals here, living here today and living in the future. And one of the questions is whether this landscape, this broader landscape of this region, can be healthy and adaptable during changing conditions. And I'll give you some examples of what I mean by that as we go along. If we go back and look here again at the variation between northern and southern Maine in winter conditions, and think about what that means for plant distribution, we can look at things like range limits of plants that live in Maine today. This figure that comes from our report includes all these spaghetti-looking lines. Are really, each one represents one woody species of plant in Maine that has either a southern or northern range limit in the state. And we can see these northeast, southwest trending ones that have to do with the elevation in western Maine, western and northern Maine. But there's this interesting loop of, very tight loop of range limits in the southern part that includes really the warm part of Maine. This is where almost all the people live in Maine, don't they? And it's where the growing season is long, the heat sum is far longer, and so forth, and it's where the ocean is warmest. And if we compare Maine to other parts of the country, we see that we actually have an extremely diverse but compressed climate in our little state. We think Maine's a big state, but actually it isn't very big compared to some of the western states. But in Maine, we have 4 degrees of latitude from north to south, and the growing zones in Maine from say northern Aroostook County to York County are the same as the ones from northern North Dakota to central Kansas. Isn't that fascinating? Who would have ever thought? And that's one of the reasons that, coupled with the diversity of geology and topography and so forth, that we have in our state, we have such rich biodiversity. It's something really unusual. And as somebody who taught field courses at the university for many years, it was so fun to be able to take students out on field trips, and just within an hour or two drive of Orono, we could be in such different environments as above tree line on Katahdin to some fascinating place down here on the coast of Maine. And it really is a tremendously diverse place that I don't think most Mainers appreciate at all in this respect. And if we think about it in another comparison, this is a figure from our report. This is looking at the same thing. The climate expanse from Maine, from south to north, is actually the same as the climate expanse in Central Europe from southern Poland to northern Finland. And in northern Finland to southern Poland is 20 degrees of latitude. And yet we have that same climate compressed into 4 degrees of latitude here. So it's very interesting for us. And we first noticed this pattern because we were looking at peatlands at one point in our studies about 25 years ago. Norm Famous, who's here, knows all about peatlands, and he was talking to us at that time. And but there are certain types of peatlands, big, simple boggy, raised bogs that live down in Scarborough and places like that, or Saco, and then up in northern Maine, very different kinds that have very complicated pools on the surface and so forth. Well, it turns out the type of pools we found in northern Maine are the same type we see up in northern Finland. And the type of peatlands we saw in southern Maine are the same type that occur, simple ones that occur in Poland. And we wondered, how could it be that we have this diversity in Maine? Well, it's because the climate actually spans that same set of conditions. It's just remarkable. So here we go, thinking about Maine in a different context. All right, I have a quiz. Many of you are naturalists and know how to identify plants. And this is a special quiz for people here at Acadia National Park in Schoodic. What is this famous Maine plant? Well, you probably, if you haven't seen it recently, good thing, because it lived here 390 million years ago. But I'm showing it to you because it raises a very interesting point about climate and the Earth's atmosphere and plant responses. This is a famous plant. It's actually the Maine state fossil, Pertica quadrifaria, it's called. It lived here during what's called the Devonian geologic period in almost 400 million years ago. And it turns out that there are some rocks of that age up in northern Maine. This odd-shaped pattern here shows Devonian rocks in northern North America. And here in Maine, we happen to have some of those. And up in a place in the northern part of Baxter State Park are some slate-like rocks that can be broken open. And inside those layers are really beautifully preserved examples of these plants which are very important globally because they were among the very first plants that came ashore when plants and animals moved out of the oceans onto the continents about 400 million years ago. These plants happened to be living here, and this is what they look like. The plant was about 1 meter high, and it looks a little odd, doesn't it? But we can see some little features here that are actually sporangia, so they're features related to reproduction. But it doesn't look quite like most plants we think of in Maine today, does it? What's missing that we would normally expect to see? What? Leaves, sure. And why weren't there leaves? Well, interesting. This is where the story connects to climate and the atmosphere. 390 million years ago, when these plants were living here, the Earth was very warm, and the landscapes, such as the ones that these were living in, were warm and wet. And the reason it was so warm is because the concentration of carbon dioxide in the atmosphere was 20 times what it is today. 20 times. That doesn't mean it was 20 times warmer, but the heat was trapped. The fact is, this story about carbon, greenhouse gases, and climate is extremely simple. The laws of physics make it extremely simple. It's not complicated the way you're led to believe sometimes. Climate is a complicated subject, but this story is actually very simple in its most fundamental and important way, because when greenhouse gases are high, heat is trapped and the Earth is warm. When greenhouse gases are low, less heat is trapped and the Earth can be cooler. Well, it happened at this time, the Earth was very warm and wet. It was warm because of the greenhouse gases. It was wet because the warmth evaporated more water from the oceans near the continents, and that moisture would be carried inland the way it is today and deposited as precipitation. So there were great swampy areas at that time. And in the subsequent couple of 100 million years, called the Carboniferous, the CO2 levels fell almost to modern levels, and within about 100 million years, which is a blink of an eye geologically, believe it or not. And but it's during that time that these plants lived here in the early stages of this period. But as the CO2 levels fell, plants had to develop leaves. Leaves evolved because as the carbon dioxide concentrations in the atmosphere were reduced by a factor of 20, the plants needed more surface area through which to absorb the carbon dioxide for photosynthesis. And as many of you probably know, the underside of leaves have openings called stomata. There are cells that control the opening, but the atmospheric CO2 is brought into those openings, and the water that's brought up from the soil by the plants mixes with the CO2 with energy from the sun to produce sugar. That's photosynthesis. And that's the exact process that led to the removal of all this carbon from the atmosphere, because as the CO2 levels were high and the plants were growing in these swampy areas, the plants would die, fall over, and because they were swampy and covered by water, the plant decomposition was not complete. Just as we get bugs developing in wet places today, when this was happening so broadly on the landscape, the forests fell over in the swamps, more forests fell over, they got buried by other kinds of sediments. And today, those buried terrestrial deposits are harvested by us as coal. That's how coal came to be there. But what happened was all that carbon that had been removed from the atmosphere in photosynthesis was put in the ground in a process that today we would call sequestration. It's the same exact thing. It's just a natural form of sequestration, removing the carbon. And at the same time, carbonate rocks were being formed. That's in a also partly biological process, removing more carbon. And in the oceans, the shallow seas around the continents of the time, there were highly productive algal communities as well. And as those algae died and fell to the sediments in the oceans, those are what later on became oil and natural gas. That's why the natural gas and oil deposits are mined out in those kind of places that were once shallow seas. So that brought the CO2 levels down to almost modern levels by 300 million years ago. The CO2 then rose during a time through some natural processes, and it was probably lucky for the dinosaurs, because when the dinosaurs, which are largely cold-blooded animals, were living, the Earth was warm enough that they could survive. They wouldn't have done very well in today's world, actually. Now, we know that in the last 2.6 million years, the Earth has had a repeated series of ice ages. We call the Quaternary ice ages. But if we look back here at 300 million years ago and ask the question, okay, if the Earth had modern levels of CO2, why wouldn't there have been ice then? If it was cold now because the CO2 levels are down, how about then? Well, there were ice ages then. This works. The story works. All right, now let's jump to the most recent ice ages. I'm done talking about hundreds of millions of years. Now I'm going to talk about thousands of years for the most part. 20,000 years ago, as you all know, Maine was covered by major ice sheets that were essentially at the peak of the last major ice age that occurred before today. And Maine was well covered. Mount Katahdin was well covered by ice. This part of the coast was well covered. In fact, the ice sheets extended all the way out to George's Bank and Browns Bank and Cape Cod and the islands and Long Island, New York. And so the features that we see on the landscape in Maine, of course, are strongly connected to those processes of the ice moving over. And in fact, that's happened, as you'll see, dozens of times in the last 2.6 million years during previous ice ages. Now, these ice ages have a regularity that's rather fascinating. I won't take time right now to explain what they are, but there are three major, what are called orbital forcing cycles that are related to the physics of the solar system, the gravitational forces of the sun and all the planets on one another, that lead to regular patterns of differences in solar radiation reaching the Earth's surface through time. And these lead to 100,000 year ice age cycles that all have a similar form. They're slightly different in detail each time, but if we look at the last 4 or 5, for example, we can see that the warm times, the top of this blue curve, is rather brief. The warm times last about 10 to 15,000 years. These are what are called interglacials, the time between ice ages, interglacials. The glacial phases actually develop slowly, often over 70 or 80,000 years, but then the glacial maxima, the times of coldest, most extensive ice, are also brief. And then there's usually a very rapid transition, or we call it a termination of the ice age, into the next interglacial. Look how tremendously rapidly we came out of these ice ages into the interglacials. And so there are lots of interesting stories here, the kinds of things that my colleagues and I have been studying. But this present interglacial, represented over here by this tiny spike on the left, is the modern interglacial that we geologists call the Holocene. It's lasted about 12,000 years as of now. And it's during that 12,000 years that everything about modern civilization we think of has developed. And that's because prior to 12,000 years ago, there was no kind of agriculture. People were hunters and gatherers, the few people who were on Earth relative to today's populations. But about 10, 11, 12,000 years ago, the people in the Middle East, and it turns out also in Central America and a couple of other places, independently invented agriculture and started domesticating plants and animals. And that allowed people to suddenly start living in congregations, in sedentary populations, and having large cities. Even 7,000 or 8,000 years ago, there were some quite large aggregations of people in the Middle East. And that meant that our social systems all had to change. There needed to be political leaders and generals and priests and college presidents and directors of institutes and all those kind of people who run things. And when that happened, it changed everything in the world as we see it today. Now, as the ice during that rapid termination of the last ice age, the ice got thinner overall from the coast inland. And about 15,000 years ago, Katahdin, this is a photo of Katahdin I took then, showing how Katahdin would have been emerging from the ice as the ice got thinner. I took this in Antarctica, of course, but it looks a lot like Katahdin would have looked, believe me. You can see the knife edge and everything, can't you? In fact, I realized recently it'd be a lot easier to climb then than it would now, too, if you could just get there. But anyway, this is what Katahdin would have looked like. And we know that the highest points on the landscape across New England came out first as the ice got thinner, because the oldest lakes on the landscape are the highest ones. The youngest ones are the lowest ones, because they were still covered by ice. And I'll give you an example from the neighborhood here in the short order. Now, we've learned a lot about the Earth's history by studying sediments of different kinds, accumulations of material that have developed in thick stratigraphic sequences. I study lake sediments, I'll get to that in a moment, but some of my colleagues, including our current Institute director who followed me, Paul Majewski, studies ice cores coming from places like Greenland and Antarctica and Mount Everest and places like that. Here's one of the ice cores from Greenland in a big project involving 17 different nations. Paul was the leader of that major research program. And these long sections of ice were collected as much as 2,000 meters below the surface. And the time span went back close to 1 million years. And some of the ones from Antarctica go back farther than that. And these are really important because they are actual records of the chemistry of the Earth's atmosphere and precipitation through time. It's an accumulation of snow that was compressed by subsequent snow, and so much that all the air was finally squeezed out and the ice became blue, hard, clear ice. But it's still the water that fell as precipitation, 897,346 years ago in this exact spot, something like that. And so it's possible to take careful samples from inside one of these cores and have pristine water that fell from the sky through time with continuous sampling, and it's quite a remarkable record. And we've learned a lot of important things from this. For example, we've learned that the pattern of carbon dioxide in the atmosphere during these ice age cycles, notice the time scales flipped around here, so it's still 800,000 years, but it's flipped from left to right this time, has the same pattern as the one I showed you a moment ago when we were looking at ocean sediments. But if we look at this pattern, it's a little more complicated. The red curve up here and overlapping with the green are direct measurements of the carbon dioxide in the atmosphere taken by modern scientists. But we only started to do that, we scientists, we as humans, started to collect this scientific evidence only in 1959. There were no records of what the CO2 levels were before that. Now, fortunately, because one strong-minded scientist from Scripps Institute in San Diego insisted on making these measurements out in the middle of the ocean in Hawaii. Within 2 or 3 years, it was clear that the trends were going up every single year. There was no question that there was an upward trend, as there almost had to be given the amount of fossil fuel being burned. And so the amount of carbon increasing in recent past is enormous. But if we look at the ice core record from overlapping ice in Antarctica that overlaps with the curve that was based on atmospheric measurements, in fact, it matches up perfectly, and which tells us that this longer record should be a reliable record. And I put this on here because I put these horizontal green lines on because these basically define what the natural variability of carbon in the atmosphere has been for, in this case, 800,000 years. The curves have now been extended back more than 1 million years, and we can say with quite a lot of confidence it's several million years that the carbon never would have been higher than this. Now, because of the industrial uses of carbon, of course, we're pushing it up very fast. We passed 400 parts per million just about 2 years ago. So this is an important record, and to put it in perspective, here's one of the figures. This is figure 5 from our report, which you're welcome to download from our website and look at. This is a figure that shows just the last 5,000 years. So this is the last half of this interglacial that we're in now. And the top curve is very important. This is the figure that shows human population through time. Of course, there weren't very many humans on Earth until, 200 years ago. And there were less than 1 billion people fewer than 1 billion until about 200 years ago. When I was a little boy growing up in South Dakota, I remember learning in 5th grade that the Earth had 2.3 billion people. And some of you my age will remember numbers like that. Of course, we now have 7.2 billion, and we're on our way to 9 or 10 billion by 2050. And this is important because the connection between human population and greenhouse gases is clear and unequivocal and very important. And we can see the carbon dioxide, nitrous oxide, of course, chlorofluorocarbons, which are a human invention, but an important greenhouse gas, very recent, and then methane, which is another natural greenhouse gas. But the emergence of the production of these by human activities is obvious, isn't it? And this is really important because with human population increasing so much, it brings home the point that this is really the story. The story has to do with human population expansion and what it means to live the way we do. And I don't mean just us Americans. There are people all over the earth who are being born, and they are going to want electricity and be able to run their iPads and all of that just as much as we do. And of course, why shouldn't they? Just to put it in a little perspective, every 5 days we add one state of Maine's population to the earth. Every 5 days. And in 1 year, we add 2 Californias. California has 40 million people, as does Canada, so you could use either example. But we add 2 Californias or 2 Canadas to the world's population every year, and those people all need to be fed and clothed and housed and have electricity and so forth. So this is the challenge. And it's very wrong, I think, to talk about controlling carbon emissions without thinking about what is really behind it. It's a much more complicated human challenge than we are even led to think about. But I think we need to focus on what the real story is here. All right, now to some interesting science related to this area. This is a photograph of a beautiful place in Acadia National Park. Many of you have been there, Sargent Mountain Pond, over at a fairly high elevation on Sargent Mountain, just west of Jordan Pond. Just a gorgeous little pond. And in 2007, a group of us hauled a bunch of equipment up the mountain to collect a sediment core because some colleagues, Steve Norton and a number of other colleagues and I, were interested in testing some hypotheses about how the geology of the water in the geology of the landscape would change as vegetation came into the landscape, and how that would change the chemistry of the water and the sediments. And so we collected a sediment core. This is a core, 1 meter long core of typical lake mud of the kind that occurs in almost every Maine lake. It's full of it's brownish greenish mud that has mostly remains of algae and zooplankton that have lived in the lake and settled out to the bottom. But at the same time, lots of fossils of pollen grains, or not fossils, they're actual pollen grains that have been fallen in and perfectly preserved. We call them fossils, but they're actually perfectly preserved biological material. And the work from this study has led to actually 5 or 6 or 7 publications by now. The first one that led to this study is this one that was published in 2011, and talk about how the chemistry of boreal lakes changed through time. And it was actually a really, really interesting study led by my colleague Steve Norton, who was here yesterday. But the pollen grains that we find in enormous numbers, by enormous numbers I mean as many as 50 to 100,000 pollen grains per cubic centimeter of sediment. These are pollen grains that have been produced by the plants that grow on the landscape surrounding the pond and are carried in by the winds and waters and give us a record of changing vegetation patterns along the lake. And by getting radiocarbon dates on the mud through different depths of time, this particular core from Sargent Mountain Pond was something like 6.5 meters long. And it represented about almost 17,000 years of time. We think it's probably the oldest lake in the state of Maine. And the reason it was established first is because the ice became thinner near the margin as it was, the overall ice sheet was melting. It was still thinner near the coast. And so the high places on the coast came out first. Well, there aren't that many high places on the coast, and the island across the way is one of them. And this happened to be a basin that could collect water and then sediments before any other site that we can think of in Maine, maybe even in most of New England. So these pollen grains then could be studied. We could take radiocarbon dates on the sediments through time so that we could establish a chronology of ages, that is, get the ages of different sediment levels from bottom to top. And then by knowing the ages and the distribution of pollen grains at one site and comparing it to other sites done across the landscape the same way. And there have been hundreds and hundreds of studies done across eastern North America, for example, using the same process so that we can map in space and time then what how the vegetation types changed over thousands of years. And these are some maps that I was lucky enough to publish back in the late 1980s that showed the changes during the glaciation from about the last glacial maximum to present of, in this case, spruces, oaks, and pines. And that's a complicated story I won't go into. But what I'd like to do is make the point that as these broad changes took place in important taxa like that, not just they changed, but all the members of their communities, the birds that were adapted to those kind of conditions and the insects and so forth also would have changed. And if we look at modern migration patterns of birds on the various flyways that cover North and South America now, we can think as the ice ages were here and covering the landscape with those big ice sheets, the birds were not having the same migration patterns, obviously. We know they weren't. And so we can speculate about what they were doing, but they've done something different. And if we play back the record through time and realize that we've had these ice ages going on for 2.6 million years, similar to the ones I showed you for the last 800,000, those kept going back. All of the plants and animals that have, and insects that had abilities to change their ranges or change their migration patterns on annual migrations had to have done so successfully because they're still here. So there's something really important. There's something very robust about the natural systems allowing them to adjust to these big climate changes. Now, of course, we're now changing climate in a way warmer than any time that's been in that past period. But when we think about some of these birds, for example, that we associate with the boreal forests in northern and eastern Maine, and why we're often involved in conservation projects that are worried about these plants and animals that relate to these different kinds of ecosystems, we can wonder how they change during times like this. Now, these maps that I'm about to show you will be in 1,000-year increments. I'm going to show them very quickly. It'll be almost movie format. And I will say the time so you don't need to look up here, but follow down here at the bottom where the green pattern shows spruces south of the ice at the glacial maximum. And the darker the pattern, the more dense the spruce population on the landscape. So I'll go through quickly and pay attention and try to look for times when everything remained stable for a while and then see how times when there were lots more dynamics. All right, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8. Now just look at this. 8,000 years ago, there were hardly any spruce here. And there was nothing resembling the boreal forest biome that we take for granted north of us across the whole of eastern North America. Isn't that interesting? The boreal forest, boreal biome did not exist at all. And that's because this was, in fact, a time when things were warmer and drier in the summertime, and there were lots of fires on the landscape. Suppose spruces and firs and hemlocks didn't do well, but pines and birches did. That's what was covering these landscapes. All right, I'm going to keep going. 9,000, 8,000, 7,000, 6,000, 5,000. Now keep an eye down here and watch the spruces as the climate got cooler and moister. Watch the spruces start to creep down into the Great Lakes and across here into New England. 5,000, 4,000, 3,000, 2,000, 1,000 today. So just the last few thousand years, the populations became to their modern limits. And very, very different from what they were even a few thousand years ago. Now, let me go back and ask you, how frequently were things stable for a few thousand years? Not much. See, the story of all of these tags, I could show you many examples of these. The dynamics of them is the story. The changes that took place in all of these populations, the distribution and abundance of all these different plant tags that changed continuously as the climate changed through this period. And the plants had to obviously adjust and try to keep up with the changing climate conditions. And so it's really a fascinating thing. If we think back and wonder about what was the forest primeval like, well, it was not like anything like it was today, even 1,000 years ago. And in fact, if we look at just the last 1,000 years, one of my PhD students, Molly Schaffler, who many of you may know, looked at some special studies she studied specifically spruce stands along the coast of Maine here on Isle Ho and down East Maine, several in the park, as well as up in northern Maine in one of the Nature Conservancy reserves, Big Reed. And, but the amount of spruce on the landscape in Maine, even 1,000 years ago, was restricted to this area right along this part of the down east coast. I'm not sure you can even see. There's a little green pattern along there. But it wasn't until 500 years ago, and especially the last 500 years, that the spruce populations became dense in northern and eastern Maine, so that the populations up in northern Maine or down east Maine, where the Down East Lake Land Trust lands are, were anything like the way they are today. Within the last 500 years, which means within just a few generations of trees. That's how dynamic things are. And this was before we started changing the Earth's chemistry. And in fact, our best estimates of the cooling conditions that allowed the southern expansion of spruce into Maine was that it probably got about 2 degrees cooler in the summertime, allowing the spruces to come down here from farther north. Now we're talking about 7 to 10 degrees warmer. So just think about this, that we don't have to be very sophisticated in modeling the plant responses to think that some of these species that are at their southern limits probably are going to have a hard time surviving and reproducing, and they'll go north, and some from the south will come up here. So it's just guaranteed there will be those kinds of changes based on just this one example I've shown you. And I could show you dozens of others. All right. This down east coast, of course, is cooler, and the reason that Molly was able to find spruce populations in this very narrow strip from essentially Mount Desert, Penobscot Bay, up towards the Bay of Fundy, was that the cold current produced by the twice-a-day tides in the Bay of Fundy bring that cold water to the surface, and then that current comes down the down east coast, gradually getting warmed by the sun, so by the time it's down by Portland and then by Cape Cod, that's much warmer water. But down here, because by the time it starts this journey to the southwest slowly along the coast, that current is so cold that for 10,000 years kept this narrow strip of land so cool that spruce could survive here, even when it couldn't survive in inland Maine. So it's a very interesting pattern we have right here. And that's because, of course, the cold water from the Labrador Sea was coming around and through this deep channel called the Northeast Channel, and then circulated up here by those high tides. All right, now let's look at just a couple of things, and then I'll wrap it up and we can have questions. There are a couple of things I'd like to show you that are happening right now in the last 50 years or so that you'll be reading about more. You've already read about some of these, and they will be important for us to all follow. And all of us can follow these in the newspaper and pay attention to what I'm about to say, I think. We've had 2 extremely warm winters in the last 4. Remember, in the year 2000, we had an incredibly warm winter all across Maine. Excuse me, almost 10 degrees warmer in every single month from December through May, compared to normal winter conditions. But that turns out it wasn't just in Maine. It was all the way across the northern Great Lakes states and the Pacific Northwest. And 2010 was the year British Columbia had the Winter Olympics. And you remember they had that horrible rainy weather. That instead of having beautiful powder snow that they would usually have, they had that rainy weather. That turns out didn't surprise me very much, because that year was an El Nino winter. The ocean current along the west coast of South America had turned off, and the water there was warm. And when that happens, I looked at the 10 previous El Nino winters, and they all looked about like this. The northern tier of states are warmer, and actually the Gulf Coast in Florida is cooler. And this is so predictable that the farmers in Florida, when they're given warning about an El Nino coming for the next winter, plant different crops, and because of it, make hundreds of millions of dollars that they wouldn't have had by adjusting to this. It's so predictable. But what's interesting is that the winter of 2012 was also almost like this. And it was not El Nino winter. And nobody really understood why it should be so warm along these northern tier of states. But one thing that came to my mind, and that of a number of colleagues, it turns out, was that, as you know, we've been losing sea ice in the Arctic Ocean at a furious rate. Since 1979, when the first satellite photos were taken and the sea ice still extended all the way from the Canadian coast all the way across to Siberia, the sea ice has been reduced by at least 40% in its aerial extent, lots of more open water. And not only that, but the remaining ice that is normally many meters thick of frozen sea ice is now only about a meter thick over most of its extent, which means that this is going from being essentially a cold, frozen continental connector on the surface. You know, the climate, the weather patterns that are produced up in that part of the world don't know there's water under the ice. They just know it's a cold, dark place in the winter that could produce these very cold air masses that would slide down into Siberia and into northern Canada and then come across to Minnesota and northern Maine. But as this becomes more open water for more of the year, the ability of the climate in the Arctic region to produce those cold air masses has to be reduced, because this is having the same kind of maritime effect that the maritime coast of Maine has, or any other part of the world. And so one possibility is that the changes in the ice and the sea ice in the north had led to changes in the temperatures. We don't know for sure if that was the explanation, but that's one of the things that we thought about. And I started thinking about these things in terms of the changing conditions that would lead to different weather patterns for us. And anybody who is involved with modeling has to describe some conditions that are sort of the starting point for a model to be run. And in the case of our weather forecast, the starting conditions, which are sometimes usually called boundary conditions, involve things like what's the temperature of the land on the earth, how much snow cover is there, what's the temperature of the seas, all the things like that. Is the surface covered by snow and reflecting heat back into the atmosphere, or is it dark and absorbing the heat? All those things are part of what our weather forecasting models use. Well, certainly one of the important factors is how much open water there is in the Arctic. And one of the things to watch in the next decade is how much this changes, because the people who are studying the Arctic Ocean right now are wondering whether we will even make it through this decade without having almost all of that ice gone. And that's because as the ice gets thinner, if this becomes much of it is only a meter thick, and there's a lot of open water, which then is essentially open fetch in nautical terms, allowing the sea winds to build waves. The high waves that can come into these thin layers of floating ice can easily break that ice up. So it's possible there could be vast expanses of ice lost in a very short time within the next few years. That'll be something to follow. And if so, these will have big influences on our climate, especially in the ends of winter, the months leading into winter as the sea ice forms late in the year. This figure shows the total amount of sea ice starting in 1979 up to the present. It's gone, there's annual variability, but it's a pretty clear trend. Another set of conditions that are related, and all of the ones I'm going to show you are mutually reinforcing one another in the same direction. So these are important. Another set are the amount of snow cover on the land surface in the northern hemisphere in the spring and the summertime. And over about the last 50 years, the amount of snow cover has decreased. Well, why does that matter? That matters because if the surface is covered by white snow cover late in the year, the incoming radiation, even as we come into the higher intensity spring sunlight, that light gets reflected black off the white surface into space and not absorbed so much by the earth. Whereas a little of it helps to melt the ice and snow, but a lot of it reflects right back into a space from the white surface. Whereas if the land surface is dark colored, then that energy is absorbed directly, and that leads to warming, more plant growth, more melting of permafrost. And you've all read about these things, melting of permafrost in the Arctic. These things are all happening together. And think about this, as the sea ice opens up and there's more open water in the Arctic, that's helping the nearby land snow cover melt sooner, isn't it? And vice versa. As that land mass melts, it's keeping the sea ice from forming as early. So these things are all working together. The temperatures over the last about 130 years of both the land and the ocean globally have been increasing. Again, there's all kinds of year-to-year and decadal variability, as there always will be in the future and always were in the past, but the long-term trends are unmistakable here. And as the land masses and water masses of the Earth continue to warm up, that also is leading to conditions that affect our weather forecasts. And so you can see why these things are working together. All right, these things lead to a variety of changes that are observed in Maine. Some colleagues have put together records that people have collected at their camps and other places of ice out dates on lakes. This is an easy thing to observe. Everybody kind of is fascinated by when the ice will go out on their lake in the spring. But if we look back into the mid-1800s at lakes from northern Maine to southern Maine, so Rangeley down to Sebago Lake, we can see that for the most part, the trend is towards earlier ice out dates. This vertical curve here is how many days into the year. The vertical scale is how many days into the year is that. And remember, in these warm winters of 2010 and 2012 in particular, Sebago never even got complete ice cover. So these things are changing very rapidly. So that's one thing that happens. Another thing that happens is that the timing of spring runoff of rivers. The U.S. Geological Survey has gauging stations on 32 rivers at least from northern to southern New England, from northern Maine to southern Connecticut. And these are arrayed in the same order. And what these patterns show here is that the blue pattern shows increases in flow on these dates and decreases in these later dates. What this is showing is a shift earlier in the spring runoff by 2 to 3 weeks. And that's no surprise. That would make sense according to the same patterns we're seeing. The exceptions to these are these rivers from Connecticut, which are just showing less runoff period in the spring. And that, I think, is because there's no longer a permanent snow accumulation that finally melts and runs off to produce canoe season down there. They just have a snowfall, it melts, another snowfall melts. And it's not till we get up into central and northern New England that we have the snowpacks that can melt for the normal spring runoff that produces what we call canoe season here. So all those things are going on together, and I'm just showing you these because there's the sorts of things you can keep track of in your lives and in the news, and think about how they're working together to affect our weather forecasts in coming years, and hence our climate, which is the sort of mean conditions of our weather forecasts. So we have the opening of the Arctic Ocean, less spring and summer snow cover, warming of the land surfaces. Glacial ice has been melting at a high rate. I didn't mention much about that. Ice out dates earlier. We have spring runoffs, longer growing seasons, which isn't a terrible thing. If we're interested in agricultural crops being grown in Maine that are different, that's not a bad thing, but it's a change, and it affects the natural vegetation as well. Continental interiors, not necessarily Maine, but in most continents, the interiors are likely to be warmer. And then we have rising sea level and ocean acidification and so forth. Sea levels were predicted a few years ago to rise maybe 2/3 or so of a meter. Now the best estimates by the people who are studying ice melting on land is that sea level will rise at least a meter by the end of this century, and it could be 2 meters. Now that's a big thing for us if we live in coastal regions, of course. And then finally, I'm going to just talk about storm intensity, because that's something we hear about in the news a lot. I'm just going to give you one last little summary bit of information here. 2 years ago, we had, just this month, we had this tremendous storm that sort of changed how people look at climate in at least the mid-Atlantic states, because they had to deal with flooding and the effect of Hurricane Sandy became Storm Sandy. But that happened just 2 years ago this month. Now, hurricanes form when the water is hot, when the ocean water is above 80 degrees Fahrenheit, or about 26.5 degrees Celsius. And that's because the energy that drives the high winds in a hurricane comes from the hot water and the evaporative water and the release of energy by the evaporating water as it condenses, rising up and so forth. But the reason that Hurricane Katrina was so strong was that the water in the Gulf of Mexico was about 2 degrees warmer that summer. Do you remember that late summer? A little bit warmer than it normally would have been. And that led the winds of Hurricane Katrina to be higher force. And of course, it wasn't the winds that did the damage, but it was the winds blowing the water into the land that caused the flooding. But this number here is very important, because if we think about the energy that goes into a hurricane from the warm water and where the warm water is, that will determine the intensity of storms at higher latitudes. And in fact, if we look at this, this is a fascinating figure, I think, because it shows a trace of cold water left behind after Hurricane Bonnie went up the East Coast in a similar fashion some years ago. This is the blue means colder water, and it indicates the heat taken out of the ocean that drove that hurricane, leaving behind cold water. And I'm sure there was also some mixing of colder water from depths, but that's a really interesting track. But this figure I'll end with shows the pattern of hurricanes in both northern and southern hemispheres, starting in the warm waters, equatorial waters, and deflecting by the Coriolis effect in both hemispheres, but deflecting to the north and east. But the most intense hurricanes, of course, are nearer the equator where the warm water is. But if the warm water, because of the warming of the atmosphere and the warming of the oceans, if the water gets a few degrees warmer farther up the east coast for us, then the intense part of the hurricanes continue farther up the coast, and by the time they get to southern New England or northern New England, they can have more energy than they do today. It's really a fairly simple relationship if you think of it in those first principles. Every hurricane has its own story, but the warmer the water is immediately south of us, the more energy the hurricanes can have by the time they get up to us, and therefore the more intense the storms. So I'll leave it at that, and if we have time for discussion, I don't know, or any interest in discussion, I'd be happy to answer some questions. Thank you very much.
We would be happy to take a few questions, and we'd ask that you raise your hand and I can bring you a mic. And if you are using this mic, please hold it very close to your chin. It works best that way.
Hi, thank you for your presentation. I thought it was really wonderful. My name is Ned. I work on a farm just up the street, and I'm very interested in the relationship between agriculture and climate, especially as it relates to the ability to support a population that is heading in the direction ours is heading.
Yep.
And I'm sort of wondering if that is commonly connected within the realm of the climate science community, and if scientists are ever going to reach the point at which they say, you know, this is a real threat to agriculture and our ability to support our population, and something has to be done, or at least, I don't know, say something about it. I don't know if it's a thing. Thanks.
Well, that's a good question. I think people are talking about it. There are people focusing on that, and the challenges in Maine are quite different from the ones that might be present in Central Africa or Central Asia or Central America, for that matter. We see the drought in the West right now. For those of us in Maine, you know, if we think about it, having milder winters and longer growing seasons isn't really the end of the world, especially since we're likely to have plenty of water. Because even with warmer temperatures and more evaporation, all the models suggest we'll have at least as much precipitation as we do now. So we could look at it for Maine as a chance for opportunities to grow different crops, have longer growing seasons, more productivity. And that's the sort of thing we actually talked about in the agriculture part of our report. You could take a look at that. But I think broadly, the issue of how 9 or 10 billion people can be fed, given the likely difficulty of having enough water in the middle of big continents that are important for producing food, is a huge issue. And people are talking about it. Many colleagues and I try to bring this issue up, and you know, I've vowed that I'm never going to talk about this subject without bringing up the people part of it, because it isn't just working on a treaty to reduce carbon emissions. You know, we are the story, really, and the way we live, and the way, even if we lived in a much saner way, with this many people, there are going to be carbon emissions, or we have a problem. So it's a real challenge for humanity to figure out how to think about population numbers that can be sustainable. And don't ask me what the number is. I've asked friends of mine who are involved in sustainability science, which is a big topic nowadays. I say, to me, the fundamental question is, what is the number? And yet nobody studies that. But it seems to me that that should be question number one. And then what do we do about that? We have a colleague named Bob Cates, who actually lives not far from here. He's a retired professor from Brown University and is MacArthur Award winner and member of the National Academy of Sciences. And he gave a seminar. He's part of our university and our institute in a retired capacity. And he gave an interesting talk last year about how would we feed 9 billion people. And there are ways, but part of the challenge of feeding people is that the reason, to go back, one of the reasons we have had the Green Revolution and produced so much food is that we have nitrogen fertilizer, and most of the nitrogen fertilizer is produced by massive uses of natural gas. That's the industrial production of nitrogen fertilizers. And natural gas is producing CO2 or methane that goes into the atmosphere, and about a third of our accumulated additions of carbon in the last 50 years is based on the production of agricultural fertilizers. So this is not helping solve the problem of the atmosphere. It might immediately produce enough food to feed more people. And it is remarkable in a way how few people are starving in the world today given how many there are and our challenges. It's one of the things that always makes me an optimist is that we are so creative at solving problems that I trust people are going to, when we have 10 billion people, there are going to be some really smart ones. And we can, and as soon as some kid in some other country or maybe here figures out the answer, they're going to spread it by some method that will have everybody on Earth know it within 20 seconds. But nevertheless, this is the big challenge. I mean, you raise a really fundamental question, and I don't know the answer because we're going to have pretty decent conditions in Maine. And I actually think thinking about water is really important for us because I will not be surprised at all that within 10 years or so there aren't tanker ships lined up off our coast to take water from here to somewhere else in the world. And we as Mainers should be thinking about what does that mean for us and how are we going to, manage our water resources without hoarding them or anything, but how this is something that needs to be thought through. There are lots of important issues involving revenue and conservation and other things. So I didn't answer your question very well, but people are talking about it a lot. It isn't ignored, believe me. More questions?
One more question, perhaps? Going?
Great. Thank you so much.
Thank you.
Thank you very much.